And so, so yeah, we're going to continue on here to our very next section. So underneath, I am going to go to page 29 in our book. And our next section is about adding forces by components. But before we start adding and subtracting the components themselves, we have to make sure that we know how to determine components. Now, we got a little bit of a taste of that in our Module 1 practice and application problems. So it's going to be very similar to that. But just want to take time to talk a little bit about rectangular components. So rectangular components are going to be when we take a single force that is not presently on the X or Y axis, and we're going to make it equivalent to what it would be on the X and Y. So we're going to break a force, capital F here, into rectangular components that are going to lie on the X and Y axis. So we're like taking one resultant force, if you would, and breaking it into components, but this time they're going to be horizontal and vertical. Okay. Now, a couple things about rectangular components. Number one, rectangular components are always going to lie on the X and Y axis. Okay. They do not float, right? So their application point, the start of their tail of their respective vectors, is going to always be at the origin where that force is starting. Okay. So if we draw our force, you're going to notice that we have these dotted lines here. These dotted lines are representing lines that are parallel to the x-axis and to the y-axis. Okay. Now they also represent, if we look at this, there's a right triangle that's developed in either side here. Okay. With the 90 degrees, in this case, in the bottom right or in the upper left. Now, force Fy, its equivalent length is to this side of this right triangle. So if we look at this as a right triangle, we have Fx, we have the hypotenuse of F, and this is an equivalent length here to determine what Fy is. But Fy is not applied out there. Fy is applied over here. And so something I see students do a lot is they will label Fy out over here. Do not do that. You need to show and label Fy where it's actually applied. That's really important because its tail is coming from the application point of the original force. Okay. And because we have the right triangle here, we now are going to have available to us the right triangle trig functions, sine, cosine, and tangent. Okay. We also are going to have Pythagorean's theorem become available to solve for maybe any unknown sides if we know two other ones. Okay. And then our same rule of internal angles are going to add to 180 degrees. So that stuff becomes familiar to us. Now, why would we want to do this? Why would we want to start with one force and break it into X and Y components? Why would we want to do that? You know, it's kind of like, why are we making more work for ourselves? We're going to go from one force to two. I heard Josh ask me before, can I do this using the rectangular component method? Has anybody ever done adding and subtracting vectors from components? Yeah, yeah. And what was nice about that? Once you get everything either on the X or the Y axis, now we can add those algebraically, right? Depending on which way they're pointing. So anything that's horizontal, because they're along the same line of action, I now have the opportunity. I'm sorry, I actually prefer that method. I know you do. Everybody does. So going forward, now that we're learning this, for those first couple problems, 1, 5, and 7, I want you to use the sine and the cosine law. All right, just practice that one on those couple problems. And now going forward, we're going to be using this rectangular component method. And the others might come up at other points, but for the most part, you're right. It's the easier one to understand, and it's usually the preferred. And even though we end up having, if you would, come up kind of more forces to deal with, they're more convenient to work with because they're along that X and Y axis. Okay, so the first part here is really just reminding ourselves the process of breaking an individual force that does not lie on the X or Y axis into its X and Y components. Okay, so as I turn here, we are going to be using application or concept application here, 2.1. We're going to practice finding the components of a force on 2.1, and then on our very next one on the next page, we're going to do the very same thing over here, is find components there. So let's start on page 30. We're going to find the rectangular components of force F, which is 800 newtons going up and to the left, and then from the horizontal, we have 35 degrees. So I am going to go to my piece of paper here. Now this is going to be another practice problem that we're going to be adding. So this happens to be, we look at our practice problem sheet. This is concept application 2.1. So add this to your notes. And this is concept application 2.1. And I'm just going to say page 30. And we're going to draw our diagram of that force. And this time it's going to be point A on that bolt. It's going to be going up and to the left. Now it's 35 degrees from horizontal. So here's our X. Now here too, again, now if you can make relatively, you don't have to be perfectly straight lines, but relatively straight lines is all I'm asking for. And then just kind of being proportion. If you do need to, grab out a protractor and a straight edge, feel free to do so. And this is going to be F is equal to 800 newtons. Try to get it straight here. Okay. And we want to find the X and Y axes here. So to do that, we're going to draw through the endpoint a construction line. I always show it dotted, and a construction line. You could show it kind of light, lighter compared to everything else. And now where it crosses over the X and Y axis, we're going to draw this in thicker, okay? We're going to start our X component at the origin A, and the tip is going to go to the intersection that was created, and we're going to label this Fx. So if you are labeling the force itself with a variable F, then its X component is going to be Fx. If you label it force A, then the X component would be Ax. We're going to do the same thing for the Y component. So I'm going to darken this in straight up. Okay. And then my tip is going to go to the intersection that I created. And then I'm going to label that Fy. So right now you should have a diagram that has 3 vectors, 3 arrowheads, 3 labels, and an X and a Y axis with your origin called out as A. Okay. So now what we want to do is we also need to add our 35 degrees. We want to add that information as well, where it's located. Okay, so now knowing the hypotenuse, we've got a right triangle here, right? There's 90 degrees right here. Do not float your Fy out here. Do not float your Fx out here. Make sure you have arrowheads. This is really important. These are not lines, they are vectors. So now that we can see our right triangle here, we have our 35 degrees. We've got a hypotenuse. Let's try to solve for our Fx first. Notice that our Fx is the side adjacent to the angle, and we know the hypotenuse. So if we're trying to find a side adjacent with an angle and a hypotenuse, which trig function, sine, cosine, or tangent, will help me out here? Cosine, exactly. So I can say that this will be my step number 1, X component. You don't necessarily have to identify what your step is. If you just want to call it step 1, that's fine. And we're going to say cosine of 35 degrees is going to be equal to, on top here, we're going to say side adjacent, which is Fx, divided by the hypotenuse, which is 800 newtons. Remember to put your units in all phases of the problem. To solve for Fx, we're going to multiply both sides by 800 newtons. Okay. And when we do that, we're going to get 655.3 newtons is equal to Fx. Okay. And then we're going to do the same thing. Step number 2 is going to be our y component. Now, as we look at the y component, the 35 degrees, we always want to use as much original information as possible. So the 35 degrees is here. We want to use the hypotenuse, even though we have, and we're probably really confident in our fx, it is calculated value. So we want to default to as much original information as possible. So I'm going to stick with my hypotenuse. So my fy would be equivalent length out here. So this would be the side opposite to that angle, knowing the hypotenuse. Which function will we use this time? Sine. Yep, we're going to use the sine function. Good. So then we're going to do sine of 35 degrees is going to be equal to side opposite, which is fy, divided by our 800 newtons. And then we're going to multiply our 800 newtons up on the other side. And we're going to get 800 times 35 sine. It's going to be 458.86. So it can be 0.9 newtons is equal to fy. Notice again, units in all phases of the problem so that when you show your final units, you can see that the newtons are left over. Okay, so any question on that one? Okay, let's do another one. Application 2.2. On the next page, on page 31. Says we have a man pulls with a force of 300 newtons. So he's pulling here. So that means that since the man is down here, the arrowhead is going down and to the right, attached to the top of a building. What are the horizontal and vertical components of the force exerted on that rope? Okay. Now, does it give us the angle? It does not. What it does give us, you'll notice this particular problem gives us the coordinates of how far over and down from that corner that our man is pulling, okay? Now, those are not going to be the magnitude of the force. Do not use those values to try to figure out what the magnitude of that force is, okay? These are distances that we need to first solve for the angle alpha. So it's really an initial step we're going to take in order to determine that angle. So let's first draw our diagram. Okay, so this is going to be concept application 2.2. We're on page 31. And this time we're starting up at point A. And I'm going to draw the x-axis going this way, our y-axis coming down this way. And like here-ish. Okay. Now the problem says that we're pulling with 300 newtons. Okay. 300 newtons. And we need to find what that angle is, alpha. All right. Now, again, we're going to use these distances. So as we look at this angle, where angle alpha is located, here's a 90 degree. This is right angle. So if I know the side opposite and the side adjacent, is there a trig function that I can use to find that angle alpha? Tangent, exactly. So we're going to say tangent of alpha is equal to side opposite. It's going to be the 6 meters divided by the side adjacent, which is the 8 meters. Meters cancel. Okay, make sure you cancel that out. Make sure you add that. Don't just put 6 over 8. Okay, it's the distance. And then you should get alpha equal to 36.9 degrees. Okay, not a final answer, but this is going to be 36.9 degrees. Make sure you show that work. Now that we have the angle, we can then proceed like we did on our last problem, where we're now going to draw our lines through the endpoint of the 300 Newton vector parallel to each one of the axes. And then we're going to draw our X and Y components. Now, in this one, they did not give a variable for the force. So in the last one, we had F, right? So we had Fx and Fy. What do we want to use for the variable for our force? We could use F again, or we could use something else. Anyone have a preference? G, let's use G. G is equal to 300 newtons. So that means that it's going to be, oopsie, it's going to be Gx and Gy. Okay. Gx and Gy. So now notice that we have each one of our vectors identified. They all have arrowheads on them and they are all labeled. Okay. Now I'm going to go down and we're going to solve for, we'll do the X component first. Okay. So Gx is the one that we want to solve for. We look at its position. We know the angle is 36.9 and we have a hypotenuse of 300. Which function? And if you're virtual, you can put it in the chat box too. I have the chat box open. So which function are we going to use to solve for Gx? Sine, cosine, tangent. Cosine, yes. Oh, don't put a, John, don't put a question mark. Cosine, do question mark or do cosine exclamation point. Oh. Definitely. Yes, we're going to use the cosine function. So we're going to say cosine of 36.9 is going to be equal to our side adjacent goes on top, which is Gx, right? Side adjacent to that angle over the hypotenuse, which is 300 newtons. Okay. So Gx is going to be, we're going to multiply that up, 300 newtons times our cosine of 36.9 is going to be equal to Gx, right? Multiplying that up. So now, should come out to be 240 newtons is equal to Gx. Is that right? Do you guys get that? Did you get it this time? Nobody's afraid to say, no, I think you're wrong, Kelly. Then we're going to do our Y component. Okay. Now this time, remember, we have our angle of 36.9 and the GY is equivalent over here, but it's not, it does not live over here. Okay. It's an equivalent length. So it would be the side opposite from the angle using the hypotenuse. Which function would that be? Would be a sine with an exclamation point, right? The sine function. So sine of 36.9 is going to be equal to GY over 300 newtons. And then solving for GY, we're going to take our 300 newtons times the sine of 36.9 is equal to GY. And we should get 180 newtons. It's equal to GY.
What would you like us to round to for the homework?
I know, that's a great question. Use your best judgment. I mean, that's what I always feel like. I think sometimes if you just say 3 decimal places or 3 significant digits, it doesn't always work. Okay. So what I like to do is inside of my problems, I like to hold a couple decimal places for sure. And we'll kind of go along as we go. So if it's maybe 10 newtons, then I'll probably hold 2 or 3 decimal places after that. If it's 100 newtons, maybe 1 or 2. If it's 1,000 newtons, maybe 1. Does that make sense? So as you kind of get bigger, you don't need as many decimal places. But yeah. I like to hold more decimal places inside of the problem as I'm working things, and I'll round my final answer. So in this case, we're not taking these any further, but if I would be using these vectors, you know, as we move on, and we will start using the vectors, I'll keep decimal places and back at this level until I get to my very final answer.
Makes sense.
I know it makes sense, but I don't know if it's very helpful, cut and dry, you know, definitive. So I always default to more decimal places. The book, you're gonna notice always 3 significant digits, and sometimes it can create some significant rounding errors.
Hmm.
So just kind of be careful. And if your answers don't match theirs exactly, it's probably because of exactly that rounding error that's going to be between the different approaches. Okay. All
Yep.
right. One more. So if we turn the page, on page 32, there's one more concept application problem. This says force F is 700 pounds. Okay, 700 pounds right here. Oh, no, I apologize. Oh, we don't know what force F is. We actually know, let's zoom in here. We know what its X component is. Its X component is 700 and its Y component is 1500. Okay. So what we want to do now is we want to find what is the resultant of those two. Okay. So get rid of this. I'm going to draw this out again. So this is concept application 2.3 on page 32. And this time we have an x-axis, we have a y-axis. We've got on our y-axis, Fy equals 1,500 pounds. And on our x-axis, we have a shorter force. Fx is equal to 700 pounds. All right. And we want to find the resultant. So we're kind of going in the opposite direction that we have been up to this point. So what we're going to do is we're going to put through the endpoint of each one of those vectors a line parallel to the other vector. So this is that parallelogram rule, but using vertical and horizontal lines. Now we're going to draw our resultant here, where we're going to start our tail at the origin, which they're calling point A, and the tip is going to go to the intersection that we just created. We're going to call this F. Now, to fully define F, we want to find what its magnitude is, but we also need to find what its direction is. Not only its arrowhead is going up and to the right, but we need to know what the angle it's at from, in this case, horizontal. All right, so to find the magnitude of F. F is the hypotenuse of what would be a right triangle here, right? If we looked at one side of it. What function, what trig function, right angle trig function would we want to use using original information to find the resultant F?
Cosine?
Did you say cosine?
Yeah.
We're going to not say cosine. Now, that doesn't mean you can't use it. I just want you to use, oh no, you couldn't actually, because you don't know an angle here. No, we don't know an angle. We can't use tangent. We can't use cosine. We can't use sine. We don't know an angle. We need an angle for each one of those.
Just the Pythagorean theorem.
Pythagorean's theorem. I heard it in the room here, and then I heard it virtually. Yes, Pythagorean's theorem. So in this case, we can say F squared is equal to we'll say Fx. Usually put the X first, right? Fx squared plus Fy squared. Absolutely, Pythagorean's theorem. So we've got sides this time, right? Now, if we wanted to find the angle, then we can start looking at the sine, the cosine, and the tangent, any one of those. But if we don't have an angle to find F as a side, we've got Pythagorean's theorem. So this is actually going to be F is equal to the square root of, and putting the numbers in place, this is going to be 700 pounds squared. Make sure you put the units in here, plus 1,500, not 15,000, 1,500 pounds squared, and both of those underneath the radical. So our F is going to be equal to, should come out to be about on 1,655 pounds. Let's see. Hmm. Make sure you put your final units there. Now, the book did it in a different order, and that's why, they use the sine function after they found the angle. But if we stick to only original information, just using those sides, this is really the better choice. All right, so now we have magnitude. We now have to get our angle to complete the direction. So angle, if we want to use original information, what's the best function to use? Tangent would be, yes, because remember, we got the two sides, right? So we would know this side, the equivalent side, and we would know the side adjacent. So side opposite adjacent. So if we say tangent theta is equal to side opposite, which is going to be our 1,500 pounds divided by 700 pounds, pounds cancel. And then solving for tangent should get 65 degrees, 64.98, right? There we go. Cool. Any questions on components right now? Rectangular components. All right, cool. All right. So as we kind of go back to our practice problems, let's see. We did 3 more. So this is our module 2 practice problems. We did 2.1, 2.2, and we just got done with 2.3 concept applications, okay? So now the next one we're going to look at is going to be that process of using the rectangular component method to find a resultant, okay? To find a resultant. So that's going to be sample problem 2.3. So I got to get back to here. Now they do a little bit of explaining beforehand, but I feel like best thing to do is to just jump in and do a problem and kind of explain as we go. All right. So, so what we're going to do is we're going to use sample problem 2.3 here. This is on page 34. And it says we have 4 forces that act on this bolt A. So we've got F1, F2, F3, and F4. And we want to determine the resultant of those 4 forces on that bolt. And we're going to use the rectangular component method. Okay, the rectangular component method. Now, the process for that we're going to go through is number 1, we're going to draw what we call our free body diagram. So we're going to draw exactly what we see here, but we're going to make it big. Okay, we're not going to make it teeny tiny in the corner. We're going to make it about 1/3, at least the top third of your page is going to be our diagram. Because then what we're going to have to do is we're going to have to add and represent, draw, and label the components of each one of those forces. So notice that we're going to be adding X and Y components here. So it's going to be adding to our drawing. So we need a lot of room. Okay. And then what we're going to do is we're going to calculate what the magnitudes of each one of those components is. And we're going to give it a sign. Okay. So that means we're going to start using what we call a convention. So we're going to apply a convention to these. So giving it a positive and a negative value. Once we determine what our values are in the X and Y total, we're then going to calculate the resultant's components, the X and Y components of the resultant. And then we're going to find the final resultant. Okay. So that's the process we're going to go through. That's kind of like high level, but let's go through all of the details. So first things first, as I said, we're going to start by drawing this diagram nice and big on the top third of our paper. Remember, we have to add labels. So do not go in a little corner. Okay. I'm literally going to use the top third. So I'm going to start by drawing an X and Y axis. I'm actually using about the top half of my page, going like this. Okay. Here's my positive X, my positive Y. My first force, F1, is 150 newtons, and it's 30 degrees from the origin. So I'm going to go like this. And this is going to be F1 is equal to 150 newtons. and its angle is 30 degrees. Kind of go in here. So in case you don't have the book in front of you, you can kind of follow along with me. My next one is going to be F2. F2 is going up and to the left. It's 80 newtons. So I'm going to go like something like this. I want to be proportional. So the 150 was nice and long. So I'm going to go 80, maybe like this. Okay, a little bit more than half. So this is going to be F2 is equal to 80 newtons. Okay, and this angle is, I'm gonna scooch it in here. I don't like being small about this. 20 degrees. It's little. And then I've got going straight down 110 newtons. This is F3. Okay. And it's going to be right along that y-axis. And then the last force that I have at 15 degrees from horizontal going down and to the right is going to be F4. And F4 is equal to 100 newtons. So what we want to do, and the point in the inside here, I'm not going to worry about labeling it because it's just going to add, you know, an extra letter, but that's that point A. They all share that origin, if you would. Okay. I'll catch up and make sure you can see this. So we want to find the one force that is going to have the same net effect on point A as all these 4 separate forces have. Okay, so we want to find the resultant, the one force. And our process is going to be, we're going to break each one of these into components, anything that's not on the X or Y axis. And then we're going to add and subtract along that to find the X and Y axis of the resultant. And then using that X and Y components of the resultant, we're going to find the final resultant and its direction, its angle. Okay, now let's draw in our X and Y components for each. Okay, now I'm going to start with 1. So F1, I'm going to draw my little construction line going down to the X axis and over to the Y axis. Now, because these would be on top of each other, I like to offset them. They're physically on the axis, but I'm going to draw my X component for F1 slightly above the axis here. And I'm going to call this F1X. And then I'm going to do for the FY the same thing just to the right of the Y axis that I have drawn. This is going to be my F1Y. So you see why we want to have some room, right? We want to make this nice and big so we can have room to actually draw these and label them. Then I'm going to do the same thing for F2. It's going to be F2X. It's the only one going to the left, so I'm just going to draw that on the X-axis. See, my 20 degrees here is, I'm going to have to draw it like down here, 20 degrees. And then my Y component is going to go just to the right, or I'm sorry, just to the left of that Y axis. And this is going to be F2Y. Okay. Now my F3 is on the Y axis already, so it does not get components. All right. Only forces that aren't already lying on the X and Y axis. And then my last one is going to be my F4. And it's going to have a Y component kind of coming down on the right side here, F4Y. And then it's got an X component. Okay. And that's going to be F4X. Now, does everybody see why we have each one here labeled the way it is? Any questions at all? So I've got in the X-axis going to the right, I've got an F1X, F4X. Going to the left, I've got an F2X. Going up on the Y-axis, I've got an F1Y and an F2Y. And going down, I've got the F3Y. and an F4, well, it's really the F3, and then the F4Y is going down as well. Okay. So now basically we start out with 4 forces and we now have 1, 2, 3, 4, 5, 6, 7 forces that we're dealing with. Okay. So we're going to find the X and Y components for each one of these. All right. So we are going to go over on the left-hand side here and we're going to say, okay, we're going to solve for all of the components. Okay. So our step number 1 is our diagram. Okay. And all of our labels. Step number 2 is going to be calculating our components. So we'll start with F1. Okay. We'll do the X and Y components. Now, as we look here, you're going to notice that we have the 30 degrees kind of at this, like, I'm going to call it the standard location. So that the 30 degrees, if I want to find the X component here, F1X, do you see how I would use the cosine function? Okay, because it's the side adjacent to the 30 degrees, it would be the cosine function. So instead of writing out cosine of 30 is equal to side adjacent over the hypotenuse, we can kind of go to that second step right away. We can say, oh, F1X is going to be equal to the cosine of 30 times the hypotenuse, which is 150 newtons. This is F1. Does that make sense to everybody? Okay. You feel comfortable kind of going there right away? If you want to write it out where it's cosine of 30 is equal to F1X over the hypotenuse, go ahead. But this is kind of doing that second step right away. So now I can just say, okay, 30 cosine 150 multiplied by, I get F1X is equal to 129.9 newtons. Now, Jack asked earlier about rounding, like how many decimal places do you want? In the problem here, what I get on my calculator is 129.9038. Okay, so stopping this at 129.9 seems reasonable to me. If I round it to 130, I'm gonna induce error because I'm gonna be using this number a little bit to add and subtract with other things. So I'm gonna add that extra decimal place. Okay. I'm gonna put just one line underneath here. Now, you might say, are we supposed to worry about positive or negative at this point? No, just magnitude. Okay, just magnitude. All right. Then over on this side, I'm going to do my Y components. So I'm going to say F1Y is equal to. So if the 30 degrees is here and the cosine was for the X function, sine would be for the side opposite, right? So I'm going to say sine of 30 times that hypotenuse, which is 150 newtons. Make sure you add the units in there. Show the units along with it. So my F1Y should be 75. So yeah, that makes sense because the sine of 30 is 0.5. And so 75 newtons for my F1Y component. Okay. Now, if I'm seeing F1Ys down here, I better see them somewhere up in your diagram, identified and labeled. Okay. All right, let's do F2. F2X is equal to, so here, now be careful. This 30 degrees was what I call the standard location, okay? 20 degrees is not. If we look at the 20 degrees, notice that it would be the side opposite. And again, I always like using original information. You could say, oh, could I use the cosine of 70? Yeah, you could. But we're going to stick with what they gave us. So we're going to recognize that, yep, this 20 degrees for the cosine, it's going to be actually, or I'm sorry, for the X component, it's going to be the sine of 20 degrees times 80 newtons. So F2X is going to be equal to 27.36. That's what I would go to, newtons. And then my F2y is going to be the side adjacent. So that one's going to be the cosine using that 20 degrees. So this one's going to be the cosine of 20 times 80 newtons. So F2y should be 75.18 newtons. Okay, now F3, we're not going to even do components because it's already on the y-axis. So we're going to skip over F3 and we're going to go to F4. Okay. So F4, 15 degrees right here. Okay, it's a small little angle. I forgot to put it in there, 15 degrees. Now that's in the standard location again, because 15 degrees is the side adjacent with the F4x. So this one, F4x, can go back to the cosine of 15 degrees times 100 newtons, which is the hypotenuse. So F4x should be 96.59 newtons. And then F4y will be the sine of 15 degrees times 100 newtons. F4y should be 25.88 newtons. So that should take care of all the components that we have. And like I said, as we're going along here, what you want to do is you want to be punching this into your calculator, making sure you get the answers, getting used to, you know, the order of things. That's something that I'm not going to say I'm not going to help you with, but I don't use a graphing calculator. I've never used one, and I've always used, kind of sounds weird, but it's a backwards way of putting things in. It's called reverse Polish notation. Okay, it used to be really popular and happened to be when I was in engineering school. So I got used to using that. So my calculator will function very different than like an IBM, like the regular ones. So you guys will like kind of put it in with parentheses and the way that you see it on a graphing calculator. So, so doing these problems along with me, making sure you're getting the same answer will ensure and reinforce, you know, how you have to put it in your calculator that I just probably won't be able to be much of help with that. Okay. And I really, you know, I'm not going to dictate what calculator you use. We're not teaching a calculator in this class. Okay. So are we all caught up? Is everybody good? Everybody have the same things that we have here? All right. So now that we have this broken into the X and Y components, we are now going to add along each one of these axes. Okay. Now, before we do, we need to add a convention. I briefly added convention, or I talked about convention earlier, but a convention is going to be something that we add to the top of each one of our problems. And it's going to tell us what's positive. Okay, so anything going to the right along the x-axis is going to be considered a positive value. Anything going on to the left on the x-axis will be negative. Anything going up along the y-axis will be positive, and anything going down is going to be negative. That's kind of our standard Cartesian coordinate system. Okay, it is. So sometimes students will ask, when you see that F2x, should I put a negative in front of that when I'm down here? No, just leave it as its absolute value. And then in the next step, we're gonna take this into consideration, which way it's pointing on the X or Y axis. Okay. And we're gonna assign a positive and a negative then. All right. So now step number 3, actually gonna kind of go down below here. So step number 3, because we're gonna keep referencing back to our original diagram. We are going to sum, I'll write it out right now instead of symbols. So we're going to sum forces in the X direction. Okay, sum forces in the X direction. And what that does is it is going to give us the resultant X component. Okay, so symbol that I'm going to use here is called the summation symbol. I think it's maybe capital sigma, I think. The Greek, is it? Okay, thank you, James. The summation symbol, and we're going to sum our forces, capital F, in the X direction. And that is going to be equal to our resultant X component. Okay, so you need to write this out to me. It's kind of like telling me what you're going to do. Okay, so then we're going to say equal to, so we're just going to kind of down at the bottom here. Now we're going to do that. We're going to sum our forces in the X direction. So we're going to look only on the X axis right now. So I'm going to start with F1X. I'm going to look, which way is it pointing? It's pointing to the right. And if I compare it to my convention, that's a positive direction, right? So I can put a positive in front of it, or since it's the first one, I don't have to put a sign in front of it because positive is assumed. But I'm going to put positive just to reinforce the fact that it's going to the right. So I'm going to say positive F1X or plus, okay? Because it's going to the right. And then I'm going to say positive F4X because that's the other one going to the right. And then now I've got F2X going to the left. What am I going to put? A negative, right? Minus, exactly. Minus F2X. Now notice we didn't put anything about F3 on this line. Why? Go ahead. It's not along the x-axis, right? There's no X component. We're going to include it in the Y though. Okay, that's where its entire magnitude is. Okay, so now what we're going to do is we're going to fill in. So this is what you're going to tell me. This is like in variable form. Summation of the forces in the X is going to give us our resultant X component. And when we sum our forces in our X, you're going to tell me what those variables are by looking at the diagram. And I should see these labeled and pointing in the corresponding directions to the positives and the negatives. That's why we have the arrowheads, right? Now what we're going to do is we're going to put our values in here. So we're going to go to our list of X components and we're going to fill in. Okay, my F1X is 129.9 newtons. So this is going to be equal to a positive 129.9 newtons. Make sure you put your units. Then I've got F4X. F4X was 96.59 newtons. And then minus F2X, that was 27.36 newtons. Okay. And now because they're along the same line of action, this becomes an algebraic problem for me, right? I just add and subtract based on their sign. So my resultant X component will equal, do this. I get 199.19 newtons. Now, if we compare to what they got, now they just did this in a little bit different format, but ultimately it's the same. You'll notice here that this is the resultant X component is 199.1. That's because they used only one decimal place for everything. We got 199.119, which is really 199.2 because we didn't round as much earlier in the problem. So you may see differences like this from your answer to the book. Call it good, okay? Don't worry about getting it perfect to their answer because the answer is they rounded to only one decimal place, which induced more error earlier, okay? All right, we're going to put a line underneath. This is not a final answer, but we're going to use it. Now we're going to do that very same thing, but this time we're going to sum our forces, sum forces in the Y direction, okay? So we're going to sum our forces in the Y direction equal, and this is going to give us our resultant Y component. So make sure you write that. So now we're going to make our list. We're going to go back up to our diagram and we're going to look vertically only. So you're going to notice we're going to have a positive F1Y, a positive F2Y, a negative F4Y, and a negative F3. So let's write that out. So a positive F1Y, positive F2Y, a negative F3, and a negative F4Y. And then now we'll put the values for each. So now we're going to go to our Y values here. So I got to kind of go on the side. So I'm going to have a positive 75 newtons, a positive 75.18 newtons, minus 110 newtons for F3, and a minus 25.88 newtons for F4Y. So my RY component, my resultant Y component, this one I got the same, 14.30 newtons. Okay. So as we look at our process, we start out with 4 forces, right? On our original diagram. We then found components of 3 of the 4, so we end up with 7 forces. And now we've reduced it back to 2 forces. Do you see that? Okay, we're on the X and Y axis now. Now, something you'll notice about our X and Y components here for our resultant. They're both positive numbers. That means that our X is going to the right and our Y is going up, because we use the positives and negatives here according to the convention. Where's my convention? What did I just do with it? Oh, it's right. Oh, it's here. Like, what the heck? Okay. According to my convention that I established, I have positives for both those resultant X and resultant Y components. That means the X is going to the right and the Y is going up. Okay. So now what we're going to do is we're going to draw these 2 components. So step number 5 is going to be our resultant. All right. So we're going to draw Y component or Y axis and an X axis. Now, as we look here, you'll notice that our X is much longer than our Y. So you don't have to draw this to perfect scale, but you want to be proportionate, okay? So we know that the X is much longer. So I'm going to draw this almost to the end here. Okay, this is going to be my X axis. This is going to be my Rx is equal to 199.19 newtons. Okay. And then on my Y axis, my RY is going to be very short compared to that X axis. So make it proportional. All right. Don't make your Y just as long as your X, because it's like, well, that doesn't look like a good representation. So think about your proportions here. So this is going to be 14.3 newtons for this one. Okay. You have to draw this representation, all right? Because now through the endpoints of each one of those vectors, we're going to draw the lines parallel to the opposite one. And now we're going to draw a resultant to point at that intersection. We're going to label it resultant, and then we're going to calculate our angle. I'm going to call that angle theta. I'm not sure what they called it, but they called it alpha. I labeled mine theta. Just label it something. Okay. So our job now is to find the magnitude of the resultant. And then what is that angle theta? What is its direction? We need both of those things to fully define our resultant. All right. So how are we going to get the magnitude of the resultant here? Let's start with just the hypotenuse. How are we going to get the length of that hypotenuse? Pythagorean theorem, exactly. So right now we have R, right? We're going to say R is equal to the square root of Rx squared plus Ry squared. All right. And we have the 2 values. So we can say, all right, underneath the radical, our X value is 14.3. Make sure you put the units in there. And we're going to square that full quantity with the units, and then 199.19 newtons squared all under the radical. So my magnitude of my resultants. Oh God, oopsie. Yeah. I got 199.7, they got 199.6, but remember their X component is different than ours, a little bit different, and that's going to be newtons. When we square the newtons under the radical, it's going to be newtons squared. And then when we take the square root, the newtons become, or the newton squared becomes newtons. So this is the magnitude of our resultant. So that's one part of fully defining that vector. Now we need to calculate our theta. How do we want to calculate theta? Tangent would be the best one. Every one of these values at this point is calculated, right? Every single one of them. The two that are the least would be the X and the Y components, right? Because we just use those X and Y components to get the magnitude of the R. Honestly, you can use any one of them, but I'm going to default to tangent as well. So my tangent of theta is going to be equal to my side opposite, which is 14.3 newtons, which is that Y component, divided by 199.19 newtons. Newtons cancel. We're going to get a decimal here, and then you're going to use your tangent function to find the angle. And the book gets that same number, 4.1 degrees. Now, when you show this angle, and when you get the resultant here, make sure in your diagram that you're identifying where that angle is coming from. That's important to me. I want to know, where do you believe that angle to be? Okay. And the same thing, if you're solving for a resultant, then we should see a vector identified and labeled as R. Okay. And if you're using FX and FY, I better see them labeled over here as well. I know it might sound like I'm being a little bit of a stickler, but I kind of am. It may not seem like, oh, why is it so important to her? This is the foundation of all of the statics. And like I said earlier, you are going to get to use all of these problems, practice problems, application problems, to use on your unit assessment. Open book, open note. So the better notes you have and the more organized and the easier it is to follow, it's going to be easier for you to work this that day. Okay, because remember, those are only one-shot deals. Okay. Any questions? So this is our process. Let's kind of peek back at it. So first is our diagram, breaking everything into the components and labeling. And then always identify, it's not a bad idea to put the convention right there right away. We did it a little bit later when we started doing our positives and negatives, but it's right away. I encourage you to only use this convention throughout this class. You really can change it to whatever you want. If you find you have a lot of negatives, like, or vectors going down and you don't want to call those negatives, you can change that convention by just changing this. But let's stick with the standard coordinates. So all of my labels, then I'm going to calculate the values of my components. I'm going to turn my page over, and now I'm going to calculate my resultant X and Y components by summing my forces in the X direction, using the convention to identify my positive and my negative here. Okay. And then putting my values in with units and then adding and subtracting. Same thing for the Y. Now I've got my X and Y components. I use those X and Y components to draw the diagram of my vector for the resultant, calculate its magnitude, and then find the angle, in this case, theta. Okay. All right. So as we look at our practice problems, I think that knocks off another one, right? I'm not going to find that piece of paper anywhere, so I'm not going to worry about it, but that's our next one. Oh, here it is. So that's this one. All right. Now, as we look at our application problems, we're going to notice that we have a couple of these in the next section that we can work on. And I think it's these coming ones that are right here. So let's take a peek at the application problems that would apply here. Epic fail here on organization. I need a better system. Okay. Components. All right. So the problems that we have assigned are 18, 19, 22, 26, 27, and 31. So from here to here are the rectangular component concepts that we just looked at, okay? Let's see what time we got, 35. So as we look here, number 18, you're gonna find these problems on page 35 in your book. So number 18 is right here. So what it wants us to do for numbers 18 and 19, which are these two problems, but you're just gonna be doing 18, it says determine the X and Y components of each force shown. So you'll notice that we have this hook. And if we would extend each one of these forces, notice that they would have a common point of application if we would move them along their line of action at the very center here of that X and Y axis. So it's kind of like what our point A has been all along. And what you want to do is you want to find the components, the X and Y components of the 60-pound force at 25 degrees, the 40-pound force at 60 degrees, and then the 50-pound force at 50 degrees. So your process would be to show the X and Y components here, label them, and then calculate their magnitude. So if we look back at the problem that we just did, this one, here it is. No, it's not that one. Here it is. What you would be doing for that problem is our first page right here. Diagram, X and Y components labeled, and then you would have the component calculations down below for each one. Okay, so that's going to be problem 218. Problem 219, very same thing. Okay, find the X and Y components of the three forces. So again, at the very center here, if you would extend these along their line of action, they would all meet at that middle point. And then you would do that same thing. You would draw your diagram and then you would calculate the components. Okay, so that's 18 and 19. The next one that you have is 22. As we turn the page, this is on page 36. 22 is referencing this diagram right here. Okay, it says cable AC, all right, exerts on beam AB a force P directed along that line AC. Knowing that P must have a 350-pound vertical component, determine the magnitude of force P and its horizontal component. Okay, now for this one, for this to support this, I don't know, it would be like a beam of some sort. You're going to notice that this is going to have to pull away from A. Okay, it's going to point up in that direction. And then what they're referring to is that's going to have an X and a Y component associated with it. So it says that the vertical component has to be 350. So that's going to be this component right here. This is going to be 350 pounds. Okay, going straight up from A. And then it's also going to have an X component coming straight down, okay? And so we want to know, what they're asking is, what is this force along that cable? And what is the horizontal component? All right. So for this one, they're giving you the angle of 55. So that would be this angle here. So then you can determine what that angle would be, right? Yeah. Okay, so that's that problem. That's number 22. Let's look at number 26. 26 says, determine the resultant of the three forces in problem 218. Oh, well, we had 218 assigned. So if we go back to 218, you did the components and now you want to find the resultant. So if we look back at this process, sounds kind of familiar. You have these two parts for number 18 done. For 26, you're then going to finish it up by summing your forces in the X, summing your forces in your Y, and then determining your resultant. Okay. Then I believe you have number 27. Number 27 on the next page says, determine the resultant. Let me zoom in here, sorry. Determine the resultant of the three forces from problem 219. Well, 219, you did the diagram, the components. Now for 19, you need to sum the forces in the X, sum the forces in the Y, and determine the resultant. So you're finishing that up with that one, okay? And then I think you might have one more problem, number 31. Okay. Number 31 says, for the post that's loaded here, determine the required tension in AC. So AC is right here. Now, this is a rope. It says it's in tension. So if it's supporting this, it must be pulling away and down towards A. Does that make sense? Okay. Now it says the required tension in AC, if the resultant of the three forces exerted at C is to be horizontal. Oh, so that means the resultant is going to be horizontal along this line, and then find the corresponding magnitude of the resultant. So this is a little bit, I'm going to say that's our challenge problem in this section, because it's not in the exact same order that we did our last problem. So you have to do a little bit of thinking. Okay. Now, this is as far concept-wise as I wanted to go today, which is far enough. Okay. We're about 3/4 of the way through chapter 2, and we have a little bit more to go, and we'll finish that up the next time we get together on Monday. But it's 7:42 right now, and we're scheduled till, I think it's 10 to 10, right? So what I wanted to do at this point was ask you first, as we look at those application problems, are there any that you want to see minus that last number 31? That one, I want you to maybe do a little bit of an attempt on it before you ask me any questions, because you might know more than what you think you know. It is in a little bit different format, but it's a good problem to do. So I don't want to do that one tonight, but if you look at 18, 19, what were the other, whatever the other ones were besides 31, are there any of those that you would want to see started this evening? Because the other thing that I was going to let you know is that if not, then you either can use the rest of this time to work independently here or virtually online. I'll be available. Or if you wanted to, work on these at another time at your convenience. It's totally up to you. Lab time is kind of open. Lecture I want you here for, but lab time you can use, as you choose. So is there any request to see any of the application problems in this next chunk? In the room, I'm not seeing anything virtually. Does anybody want to get any assistance starting any of these? You want to look back at those most recent sample problems or concept applications, and those are going to be what's going to help you through. If not, then what I'm going to do is I'm going to stop the recording at this time, and I'm going to let you guys kind of do with this time what you want. If you want to continue to work independently, that's totally fine. If you want to be done for the night, that's totally fine too. I don't want anybody to feel like they can't do that. So I'm going to stop. Let me know if you need me.